Today we'll be discussing the quantum mechanical harmonic oscillator, and this is going to be the quantum model for vibration, and it is called the simple harmonic oscillator, abbreviated SHO. So, in a chemical bond, there exists an equilibrium bond length for which the potential energy of the system is at its lowest, and this position is found at x equals 0. So, if we take a look at our energy well, we can see that at position 0, that is where it's at its lowest potential energy, and that is the equilibrium bond length. Remember, for HCl, this was something like 1.275 angstroms. So at the lowest energy of the well, that's where it's at its most stable. So for the classical harmonic oscillator, we saw that potential energy V can be described with the equation 1/2 kx squared, where k is the spring constant. So given this equation, its shape would be a simple parabola. And we see that on the left here in blue. The classical harmonic oscillator starts here in blue, and it's just a nice parabola and ends over here. The simple harmonic oscillator, its shape is a little bit more complicated. And this is our energy well shape, where it's asymmetric and a little bit strange. This is called the Morse potential. So the energy well is synonymous with the Morse potential. Now, when comparing the classical harmonic oscillator and the Morse potential, we can see that there's relatively good agreement in this area around 0, and it diverges as we go up in potential energy. But down here, around the point where we have our equilibrium bond length and the potential energy is at its lowest, the classical harmonic oscillator and the Morse potential are generally sort of the same. So they agree near equilibrium. So that's going to be important because later on it's going to allow us to use this equation for potential energy given that we're near the equilibrium. So, since we're talking about a quantum mechanical model, let's use the Schrödinger equation. So, bringing it back, we have h psi is equal to E psi, where h, our Hamiltonian operator, is going to be equal to negative h bar squared over 2 times the mass times the second derivative with respect to x plus the potential energy. And so when we apply that to the wave function, we can distribute the operator, and what we get is negative h bar squared over 2m times the second partial derivative with respect to x of the wave function plus potential energy times the wave function is equal to energy times the wave function. Now, we can substitute in this equation for potential energy, 1/2 kx squared, where k is the spring constant. What we're going to do is simplify the equation just so that it looks like this, kx squared over 2, and we plug it in for v, and we get equation 7.29. Negative h bar squared over 2m times the second partial derivative with respect to x of the wave function plus kx squared over 2, which is our potential energy, times the wave function is equal to energy times the wave function, our eigenvalue and our eigenfunction. In the simple harmonic oscillator, just like in the particle in a box model, the identity of the wave function equation is dependent on n. And n, of course, relates to energy. These things are all interrelated. So if we take a quick look back at the particle in a box model, we can see that psi sub 1 of x is equal to a times sine of 1 times pi times x over a. Psi sub 2 is equal to the same, except in our numerator we have 2. And psi sub 3 is the same, except for in our numerator we have 3. Now, in the simple harmonic oscillator model, our wave function is going to change based on our n value. And even though the word simple is here for our model, these wave functions are anything but simple. So here we have equation 7.30, our wave function. And that is psi sub n of x is going to be equal to a sub n times h sub n of alpha raised to the 1/2 times x times e raised to the quantity negative alpha x squared divided by 2. So n can be an integer value is equal to 1, 2, 3, or any other integer value. This entire species here is our Hermite polynomial function. So this is a function. This is h of alpha raised to the 1/2 times x. So h times alpha, or h of, rather, alpha raised to the 1x. So this expression here is the Hermite polynomial function, h of alpha raised to the 1/2 times x. So this is not a variable times an expression in parentheses. This is a function, and it's the Hermite polynomial function, which we'll get a little bit more on in a second. Our alpha is just a combination of constants. That's the square root of the spring constant times the reduced mass divided by h bar squared. So our alpha, as we see in the future, is not really going to change. It will affect our wave function depending on what the masses of our systems are, but for the equations, alpha is just a combination of constants that is independent of n, and so we're going to just keep alpha as alpha. A is our normalization constant, and that is equal to this expression here, 1 divided by the square root of 2 raised to n times n factorial. So that's the first time that we've seen a factorial in this class, multiplied by alpha divided by pi raised to the 1/4. So let's get a little bit more information on what Hermite polynomials are. What these are a series of polynomial functions that are orthogonal to one another on the interval -infinity to +infinity. So these were derived in the early 1800s and are just a series of orthogonal polynomial functions. We won't derive them, we will just be using them in this class. And so you can see that as follows: when n equals 0, h sub 0 of y is equal to 1. When n equals 1, h sub 1 of y is equal to 2y. When n equals 2, h sub 2 of y is equal to 4y squared minus 2. When n equals 3, h sub 3 of y is equal to 8y cubed minus 12y. When n equals 4, h sub 4 of y is equal to 16y to the 4th minus 48y squared plus 12. When n equals 5, h sub 5 of y is equal to 32y to the 5th minus 160y cubed plus 120y. So these are just identities of Hermite polynomial functions, and we will be using them on the next page. Our wave functions for the simple harmonic oscillator change, and they are dependent on n. And so what you see here in this energy well are our psi of 0, 1, 2, 3, and 4. These are our wave functions for the vibrational model. And their identities are as follows. We start with psi sub n of x is equal to a h of alpha raised to the 1/2 x times e raised to the alpha x squared over 2. So this is our general formula, and here are the identities based on which energy level we're at. So at n equals 0, psi of 0 of x is equal to alpha over pi raised to the 1/4 times e raised to the negative alpha x squared divided by 2. Not so bad, pretty simple. For n equals 1, psi sub 1 of x is equal to, we have a coefficient now, 1 divided by root 2. Alpha over pi raised to the 1/4 stays the same. Now we have an expression here, so multiplied by 2 times alpha raised to the 1/2 times x times e raised to the negative alpha x squared divided by 2. For n equals 2, we have psi sub 2 of x is equal to our coefficient 1 divided by root 8 times alpha over pi raised to the 1/4 times the expression 4 alpha x squared minus 2 times e raised to the alpha x squared divided by 2. And finally, we'll be using n equals 3, and that is psi sub 3 of x times coefficient 1 divided by root 48 times alpha over pi raised to the 1/4 times the expression 8 alpha raised to the 3/2 times x cubed minus 12 alpha raised to the 1/2 times x multiplied by e raised to the negative alpha x squared over 2. So you'll probably see a pattern where e raised to the negative alpha x squared over 2 and alpha over pi raised to the 1/4 exist in all of our wave function equations. So really the only things that are changing are whether or not we have a coefficient and whether or not we have an expression in the middle that contains alpha and x. So to see where two of these equations come from, we're going to derive the equation for psi sub 0 of x for n equals 0. So first, we begin with our equation psi sub n of x equals a times h of alpha raised to the 1/2 times x times e raised to the negative alpha x squared over 2. So the first thing that we're going to do is get rid of the a. These are going to be our normalization constants. So we're going to substitute a sub n is equal to this expression here. So that whole thing is going to go right here. Next, we're going to use our Hermite polynomial function. So the function here is h sub n of alpha raised to the 1/2 times x. So this whole thing is a function. And so we're going to use our function as an example, h sub 0 of y is equal to 1. So this expression is just coming back from the fact that we are at n equals 0, and the identity of the Hermite polynomial function is shown here. H of 0 of y is equal to 1. So we're just going to use that equation. Now, we have 1. Do we substitute y is equal to alpha raised to the 1/2 times x? No. Our solution does not contain y. So this solution 1 has no y variable in it, so we're done. Our h sub 0 of alpha raised to the 1/2 times x is just equal to 1. So when we have our entire expression here, our function, that whole thing simplifies down to just being 1. Now the next thing we're going to do is substitute for n. So n is equal to 0. We're going to substitute that in, and that shows up for our coefficient. So now 1 is going to be divided by the square root of 2 raised to the 0 times 0 factorial. 0 factorial is 1, 2 raised to the 0 is also 1. So this whole coefficient here is just going to simplify to 1. Our Hermite polynomial function is 1, and so our whole expression for the wave function simplifies down to psi sub 0 of x is equal to alpha over pi raised to the 1/4 times e raised to the alpha x squared over 2. So if we were to flip back a page, we would see that this answer here matches our given wave function equation for n equals 0. Moving on, we're going to show the derivation now of psi sub 1 of x, where n is equal to 1. So what we're going to begin with this time is having already made the normalization constant substitution. So we've already assumed that we've brought in this expression here for a, and that's where we're going to begin with for our derivation of psi sub 1. So psi sub n of x is going to be equal to this whole expression times our Hermite polynomial function times this expression e raised to the negative alpha x squared over 2. So now our first step is going to be to use the Hermite polynomial function. So from our identity of n is equal to 1, we have h sub 1 of y is equal to 2y. So that is just a given expression. So with h sub 1 of y is equal to 2y, do we need to substitute y is equal to alpha raised to the 1/2 times x? Yes, we do, because our solution 2y contains the variable y. So we make that substitution and we get that h sub 1 of alpha raised to the 1/2 x is equal to 2 times alpha raised to the 1/2 times x. And so we plug that in for our Hermite polynomial function, and we get this expression here in parentheses. Our next step is to substitute n is equal to 1. When we make that substitution, we have our coefficient is 1 divided by the square root of 2 raised to 1 times 1 factorial. And so this whole denominator is going to be, or inside the square root is going to be equal to 2. And so our whole coefficient simplifies down to 1 divided by root 2. And so psi sub 1 of x is equal to 1 over root 2 times alpha over pi raised to the 1/4 times 2 times alpha raised to the 1/2 times x times e raised to the negative alpha x squared over 2. And if we flip back again, we can see that this expression matches well with our given expression for n is equal to 1. Again, the only thing that is changing is our expression for the Hermite polynomial function and our coefficient. So moving on, we're going to now talk about the simple harmonic oscillator eigenvalues. So equation 7.33 gives our equation for the eigenvalues. So now our energy has different equations. And so energy based on n is going to be equal to h bar times the square root of k over mu, which is the spring constant divided by the reduced mass, times the quantity n plus 1/2, where n is equal to 1, 2, 3. So this is showing that this is quantized energy. The energy gap also has another definition, and that's based on the fact that our energy gap can absorb light, and so our energy gap, again, can also be equal to h nu times n plus 1 over 2. So this is similar to what we saw with Planck's equation, energy equals nh nu, showing that energy is quantized, for n is equal to 1, 2, or 3. To isolate the variable nu, we can set these two equations for energy equal to one another, where we have h nu times the quantity n plus 1/2 is going to be equal to h bar times the square root of k over mu times the quantity n plus 1/2. The n plus 1/2 expressions on both sides of the equation cancel, and what we're left with is h nu times h is equal to h bar times the square root of k over mu. We rearrange and find that mu is equal to h bar over h times root k over mu. We can substitute our expression for h bar, and we get that nu is equal to h over 2 pi times 1 over h. And those Planck's constants cancel, and what we're left with is equation 7.34, the frequency of oscillation. And so we can actually identify the equation for frequency for the simple harmonic oscillator, and that is equal to 1 divided by 2 pi times root k over mu. Now we will move on and talk finally about the simple harmonic oscillator expectation values and probability. So the expectation values for potential energy and kinetic energy are equal. So I'm going to bring back the picture showing our energy well at the very bottom, and here we have our wave function equations shown as waves. So if you recall from the particle in a box model, where the expectation value of A was equal to A over 2, so that is right in the middle for our waves. So for each of these waves, right in the center is our expectation value. So the most likely place to find, or the average value of the wave. And so that is describing the expectation value for kinetic energy, right? Because inside the well, what we have is kinetic energy. Now we can also look at the parabola that describes potential energy. Now, where would you expect to find the average value for potential energy? Well, since we have equal and symmetric values for potential energy on either side of the center, we can also expect to find the value for potential energy to be right in the center. So we can set the expectation value for kinetic energy equal to the expectation value for potential energy, and that whole thing is going to be equal to h bar over 2 times root k over mu times the quantity n plus 1/2. Now, why is it h bar over 2 when in the energy equation it was just h bar? Again, that goes back to the fact that we're finding it right in the middle. So the length divided by 2. Moving on to probability. Probability will be generally pretty straightforward, where it's the wave function squared of x, the integral of the wave function squared of x times dx. So if we were to take our wave functions and square them, they would all look like this. Now the interval is from negative change in x divided by 2 to positive change in x divided by 2. That's just saying that if we start in the middle and define that as x, we have a change in x going over here and a change in x over here. So that is our entire interval, delta x. Divided by 2 is the left side, divided by on the negative side, and divided by 2 positive is on the right side. So from here to here would be negative delta x over 2. From here to here would be positive delta x over 2 when the entire distance is delta x. Now, similar to the particle in a box model with a finite depth, the amplitude at the walls are non-zero. As you can see here, they're not zero. For the normal particle in a box model, they were standing waves that existed at an amplitude of 0 right at the edges. But for the finite depth, which is a little bit more realistic, we see that there's a non-zero amplitude at the walls. If you recall, for particle in a box, this allowed tunneling. As the spring becomes stiffer, the value for k, our spring constant, increases, and particles become more constrained. So that has an effect where we end up getting a higher probability at the walls. So now, some noticeable differences between the simple harmonic oscillator and particle in a box. Our first is that the harmonic oscillator has a much more complicated box. So we have a well instead of a box, and this has some side effects of giving us more complicated wave functions. Our waves are not simple wave functions, so they change based on which n value we are at. The probability density depends on position, and the probability is greater at the walls. And it is much more obvious the higher the n value you get. So you can see that for n equals 4, we have a higher probability at the walls than we do in the center. The expectation value is still in the center. Remember, this is the average position, but the probability is greater at the walls. And finally, energy spacing in the simple harmonic oscillator is consistent between energy levels. On purpose, you can see that the difference between these energy levels are all the same.